attend my talk. I hope you're all enjoying the conference so far. My name is Ravi Srinivasan. I work at Red Hat, 20 plus years of experience in the industry. I basically work in our products and technology learning, which is we are responsible for creating the trainings. I think the previous speakers mentioned the DO316 is something that our team created. So please go check it out. And we have other trainings for other Red Hat products also. Although this talk is going to be more community, focused on Istio service mesh. So in the past, I've mostly focused on app dev, cloud native development, DevOps, Linux and open source user for a long time. So I've originally designed this particular session, assuming a lot of college students would be there. So can we do a quick show of hands? How many of you, I'm assuming based on the previous session, many of you are familiar with Kubernetes and OpenShift, right, to an extent. How about service mesh? Have you guys heard about it or worked with it? How many? No one? Good. Okay, good. So I'm hoping, it's a lengthy demo. We'll see how much we can get through. I'll show you a few use cases. So some interesting takeaways, some interesting developments have happened in the service mesh landscape. So I'm hoping you can take this away and do further research and decide on suitability on your applications, on whatever your infrastructure that you have. So quick agenda, brief introduction to Istio Service Mesh, its architecture, some use cases, and then we'll quickly jump into a demo, and then hopefully we'll have time for Q&A in the end. So before diving into the architecture piece, in an ideal world, right? So I'm speaking as an application developer, right? In an ideal world, application development is a complicated topic, right? We are busy with requirements, market changes are coming in, bug fixes, and if you're working in the, for example, financial services industry, you have regulation, to take care of. We have our hands full. So in an ideal utopia, right, you'd have, of course, you'll have microservices, right? We're all doing microservices nowadays. Business logic, you focus should be on the business logic. Some utility libraries maybe you'll package up in your microservice, and that's it, right? That is the developer's world. But reality, reality isn't that straightforward, right? You'll have what is typically called these non-functional requirements, right? Security related and traffic handling, observability, a bunch of other things, right? And then the genesis of this whole service mesh concept was, do we really need to, have developers handle, all this stuff? So I think 10 years ago, if you've worked in this microservices and APIs and this landscape, there were a lot of libraries, language-specific libraries like Spring Boot. If you worked with Spring Boot, it had libraries to do all this, fault management, request throttling, a bunch of things. But you need to include it. You have to include a library in your code, and if something changes or some configuration changes, you'll rebuild them, recompile them, and then redeploy them, right, on Kubernetes. So the thinking started: can we offload some of this to Kubernetes itself, right, or some other system running on top of Kubernetes? That's where this whole idea, began. And then Istio is one of the most popular open source service meshes. IBM, Red Hat, and Lyft, LYFT, US based. They're like Uber in the US. They were big. They are still big. This is where this whole thing started. Lyft had hundreds of microservices running on thousands of servers, handling all sorts of peak traffic. And then they were having trouble because features were coming in and they were adding, they were growing, and new features were coming in. Developers really struggling to manage the load, traffic spikes, as well as also keep up with application requirements. So this whole thing led to the start of the Istio project. Zero trust network. I don't know how many of you are aware, but certain industries mandate that if you have a cluster of 3 nodes, for example, and when they communicate, that communication should be encrypted. And then there's all sorts of authorization policies. They'll tell you there should be zero trust. By default, deny everything. Only allow services which you allow, and they should be configurable. And sometimes, most of the time in the old days, this was done in code, which is very painful, right? Because nowadays you're rapidly bringing on new application, new features, new APIs. You can't keep rebuilding code and redeploying it every time something changes. Traffic control, again, I said, so Lyft, if you take, for example, right? So on certain days where they have baseball games or football games, massive sudden traffic, and then they need to figure out some way where they could respond quickly. And then they started adding other food delivery service, typical like what, the same thing what we do here, right? Once you start a platform, new features keep coming in, they look for ways to exploit, based on things. And you can't predict this upfront, right? Like when you design the microservice today, if you're Swiggy or one of our, right, they started actually with food service, but then look now, they're doing delivery, parcel, all sorts of things, right? You can't predict from the get-go that I'll need these features. All of this was incrementally added. So you need an infrastructure platform that can respond to all of this stuff, right? Application observability, there are multiple talks in this conference, open telemetry and Prometheus and all of these tools. Istio also is uses open telemetry standard underneath. We'll see more detail in the demo. And then it's designed for running natively on Kubernetes. So it is very tightly integrated with the Kubernetes APIs. So you can start, you don't have to, it's not all in, right? You don't have to, you can gradually, incrementally adopt service mesh features piece by piece, right? You start deploying your microservices on Kubernetes, and then slowly, incrementally, you can adopt service mesh features, right? A little bit of a marketing talk, but I'll quickly run through the bullets. So like I said, some distributed system challenges, the fallacy of distributed computing, you would have seen these bullet points, right? Network is reliable, and a whole bunch of other corollaries. So what if, instead of writing code for it or throwing in a library, which is different for different platforms, right? So I'm assuming you're deploying microservices using different languages, right? JavaScript, Spring Boot, Quarkus, whatever, .NET. And if you want to handle it at the library level, it's still a pain, right? You need to track these libraries, package it, figure it out, maintain the life cycle and all that. What if, you offload it, to a layer lower than that? Some way to enforce common policies across services, right? You'll get a better understanding when I run through the demo. Allow developers maximum to focus on business logic and not worry about, networking related stuff and security and authorization policies as it relates to a network, right? Reducing boilerplate code. So there are multiple ways to achieve this. It's not like unique to service mesh or anything like that. Like I said, there are libraries, there are other systems, but it checks all the boxes with one common layer, right? Like I said, it's natively integrated with Kubernetes, as there are some CRDs that service mesh has created, which gets installed, and then you manage the service mesh policies just like you would do any Kubernetes resource, YAML files. And also, there are a lot more features which are not listed here. Particularly useful are these ingress and egress features. Some of it you can do at the Kubernetes level, but I believe service mesh does it in a less intrusive, less complicated, much more easier way, right? So you can control both ingress and egress. Like I said, if you are working in a compliant, industry which has a lot of compliance, they will say you must deny all egress traffic and allow only what that particular application needs or what it is, right? So no outgoing traffic allowed, only what the administrators configure should be allowed. Either it's host name or, it gets very ugly if you go into IP ranges, but typically host names, that's how it is. So very quickly, the Istio architecture is based on a concept of a control plane and a data plane. Control plane you all already know. If you're Kubernetes, control plane is the API server. Same thing here. A daemon set called Istio D is the control plane, where this is where all the configuration, all your YAML files are passed, read, validated, and then that propagates it to what is called as a data plane. So what is a data plane here? So service A, B, C, D in this diagram are your microservices, right? You've deployed them on Kubernetes, they're running happily, and once you enable the service mesh, what happens is this sidecar pattern. You all would have heard sidecar pattern. So what happens is within a pod, these envoy proxies get attached and they intercept all network traffic. So this is how service mesh achieves what I said in the previous slide about ingress and egress, right? So any traffic that comes in, goes out, goes through these envoy proxies, right? And envoy was created at Lyft, I say. Also, Google has adopted it for their GCP control plane background. So it is very, very, battle-tested, mature project. It's written in C++, so it's very, very fast. Like Nginx HA proxy is one of in that family of proxy servers, but you can use it for multiple purposes. It is used for multiple purposes in other open source projects. And one of the biggest pain points for people who have done this in the past, right? Mutual TLS. One-way TLS, easy, right? You install a certificate, you're happy. Again, like I said, certain industries or certain applications, they will mandate that all communication should be encrypted both ways. So server should verify client is valid, client will verify server is valid. Mutual TLS. And if you do it in the olden way using VMs, the horrible, you need to generate certificate, copy them to the right place, it will expire, you need to rotate them, all this, hassle. And service mesh solves it in a very elegant way, right? It comes with its own CA certificate thing, which issues temporary certificates and rotates and expires, so you don't have to worry. You don't have to manually control them, is what I'm saying, right? At the flick of a button, you will get mutual TLS without changing any application source code or creating any certificate or anything like that, right? Very elegant. One of the number one reasons why service mesh people adopt for mutual TLS. The sidecar mode, what I mentioned previously, was the default. It's stable, it's mature, it's been there for many, many years, is what many production deployments run. Interesting recent development, only last year, November 2024, they introduced something called ambient mode, right? So if you notice the previous, every service you deploy will have a sidecar container, right? Sometimes this is overhead, and it complicates matters a little bit. Although it is transparent from you, like you don't manually do anything, it will inject the sidecar automatically. You don't have to configure any YAML for that. It's still, if you have 100 microservices, there'll be 100 sidecars. There are literally another container running within the pod. So they came up with a better ambient mode data plane, which is running slightly differently, right? So there are no more sidecars. You have something called a Z tunnel written in Rust, which handles layer 4, MTLS traffic. And there is only one Z tunnel per node. So if you have 3 node cluster, there'll be 3 Z tunnels, right? And then for layer 7 HTTP related stuff, you have another specialized envoy proxy per namespace. It can be one or more. Same thing with Z tunnel. It's a pod after all, running on Kubernetes, right? So I think we'll run out of time. So rather than talk about use cases in slide, I think I'll show you in the demo itself, right? The demo is a bit long. Like I said, we'll run through as many use cases as possible. Hopefully, we'll have time for questions, but you can ping me offline also, rsriniva@redhat.com, and we can discuss. So before that, let me show you the setup for the demo. So what we have here is a very simple hello world type application, a set of microservices. So I've deployed 4 microservices, right? Service A, B, C, and D. Right? These are my microservices. They're all hello world type. And then you have something called BFE, which is backend for front end. It's a proxy, like very common, in enterprise, cloud native type, applications. You will have a backend, BFE, backend for, a backend proxy type thing that will front calls for all the other microservices. It's an orchestrator. You can say it composes and orchestrates other microservices, right? So you have these 5 native Kubernetes things, services running on my, I have Minikube running here locally, right? So I've already installed Istio and done a whole bunch of boilerplate stuff. So in the Istio system namespace, you can see the service mesh related pods are running, right? So you have a CNI pod, you have Istio-D, which maintains it's a control plane basically. You have Kiali and Prometheus. Kiali we'll see in the demo. It's a traffic visualization, web-based console, Kiali. Prometheus, you all know, it scripts metrics from all the microservices deployed on Kubernetes. The Z tunnel, I told you, in ambient modes. We are running in ambient mode. I'm the demo running in ambient mode. Another pod for Z tunnel. And then we have the 4 microservices running here, ABCD. We have the BFE, right? And then there is this thing called a gateway, which is another specialized Envoy proxy, that service mesh, you need to configure it to let traffic come into the cluster, right? And I have some curl thing to do some testing for testing purposes, right? So what we need to do is first I will port forward the backend for front end so that we can access it over localhost, right? So let me do this. So let me show you this thing first, the code, right? So very simple, right? Just hello world it sends, right? So traffic comes in through the BFE gateway, like I said, the root endpoint. It just says hello from BFE, right? If you call service A, it's like an API gateway, right? If you have done it on AWS and I think it's the same way, right? Based on certain URL pattern, it will redirect. So if you hit service A, it will send it to service A. You send service B, it sends it to service B, so on and so forth, right? Service C goes to service C. Service C further service C is acting as like an internal proxy. I just did it for demo purposes. It just calls service D, right? The reason for this will become clear as we proceed. So you notice I've not installed any libraries specifically for service mesh or anything for traffic, security, nothing. Right? It's basic packages. And I've just chosen JavaScript Node.js here for simplicity's sake. It could be you could write this microservice in any language you want. Funda is the same. There is no specific. If you take Java, I don't have to install an Istio service mesh specific library or anything like that, right? This is the BFE gateway, description file. It just says, yes, it listens on port 80, and then basically we are saying any traffic that comes into this gateway, just send it to BFE. That's all, right? Very simple. So it's a sort of a gateway, a standard gateway that works the same on all platforms. It's a Minikube, whether you run it in AWS, the Funda is the same. It's like a gateway light. Doesn't have all the features of gateway. You'll still use the AWS ELB or whatever GCP has, whatever Azure has. And this is a way to get traffic into the cluster. That's all. It's actually based on the gateway's API CRD, which is new in Kubernetes, to replace the old ingress API. So that's it for the application. So we've done port forwarding now, right? So as usual, like I said, root will get corresponding requests are called based on what you say. So if you call C, obviously it will just proxy the call to service D, right? So that's all here. Now what we'll do is we'll deploy. I have only one version of service D, right? So let's deploy a version 2 of service D, right? Let's see if it's running here. Right? Okay, service is running. And so it's typical, your classic Kubernetes behavior, right? Where it is load balanced almost equally, 50-50 round robin load balancing between V1 and V2, right? So far, nothing, no surprises. It's the Kubernetes we love and know. Everything is the same. And now I will enable the service mesh ambient mode. You do that by namespace labeling, right? That's all. The moment you label it, right? And then we'll install this waypoint proxy that I showed you in the architecture diagram, right? So this is how you incrementally enable stuff. So I've deployed the services, vanilla Kubernetes behavior. Now by namespace labeling and this command, Istio command. The Istio is like a server daemon, control binary for service mesh, and it works the same across all platforms. This is not specific to Minikube. It will work the same whether you deploy in AWS, GCP, Azure, anywhere where Kubernetes runs. The command remains the same. So now, if you notice, we should see a pod for the waypoint proxy, right? So waypoint proxy is for layer 7 stuff. You want to pass HTTP headers. You want to do something which is just beyond, source and destination IPs. In that OSI layer thing, Z-tunnel handles layer 4. Waypoint handles layer 7. So we'll need it for certain use cases that we want to implement here, right? And then we can start visualizing in Kiali. So there's one port forward here, one port forward for Kiali. Right. So this is the Kiali. I will go to traffic graph, version app graph. I'll enable certain things so that we can see stuff. So currently there's no traffic. It is empty. Let's start sending traffic. I'll send 100 requests to service C. Right? So equally load balanced. And then what's happening here is all the requests are going in, right? Service mesh is capturing it in Prometheus, and the workflow is a little bit async, so you won't see it in instant real time. It is getting stored in a Prometheus node somewhere, and then you'll see this. Is the font? So you can see it shows you approximately, right? These are heuristics. It's not an exact value. You can see that it is split almost 50-50%, right, between V1 and V2. So this is how the traffic is coming in. It's coming in through the gateway, hitting BFE, the backend front proxy, which sends it to service C, right, and then which calls service D, and then they're equally split, right? That's what you can see here. And you see these green locks in between. That just says that communication between the services is mutual TLS encrypted without doing anything, no certificate, nothing. I didn't run any SSL commands, copy stuff, nothing, right? So very easy to turn on mutual TLS, instant win. Doesn't matter what language the microservice is written in. Doesn't matter how many nodes it is running. This is just Minikube on one node, right? It works the same whether you have multiple nodes. It works exactly the same, right? The node to node, the service to service communication is mutually encrypted automatically, right? Now let's try another thing. So before I apply this, I will show you what we are trying to do here. So currently the default behavior is what is my file name? Split traffic. So what do we have behavior so far? 50-50, it is getting split between V1 and V2, right? No change, default Kubernetes behavior. Now we have created what is called as subsets, right? All this says is, it is saying send 100% of the requests to V1 and don't send anything to V2, right? Let me show you first, and then I'll tell you where it comes in handy, right? So we'll do that and then start sending. So you notice all the requests are going only to V1, right? Again, no source code changes, no redeployments, nothing. What is the secret here? All the Z-tunnel and the waypoint proxies are intercepting all the traffic, and they're doing it in a Kubernetes native way, right? They're just working based on the service concept, right? Service A, service B, service D, no hard-coded URLs or anything like that, just based on the service name. And if you notice, right, only one version. Before it was going to 2, now it's going only to 1, right? So where does it come in handy? Let's say V1 is your currently deployed in production. V2, you're testing, right? New version of your application. But you're not confident, you don't know how it's going to behave. So is there a way to send 90% of the requests to V1, which is your stable production? Nobody. 10% of the requests, maybe we can send it to V2, test it before we are confident, and then we'll make it, round robin, 50-50, whatever it is. Again, no source code changes, right? No redeployments. So that's what the next use case is about. Split 90-10. Right? Where is that? Well, you have to just change it here, so we can do it right here. I'll do that, and I will just say replace, right? These are all standard kubectl commands, right? And then I'll wait for some time, keep sending it, request. Now you notice 90% of the requests are sort of going to V2. It takes time to, propagate the policy and for the, thing to get working. But you notice, yeah, it's going to Prometheus and then coming async. But you notice again, heuristics, right? Roughly now, 90% of the requests are going to V1, 10% of the requests are going to V2, right? Very, very handy feature. And then you can progressively change those values in the YAML file I mentioned, right? To adjust whatever you want. Let's say you have a catastrophic failure in V2, right? And just flip it back, 90, make it 100, 0, 95, 5, whatever you want, right? Very useful feature, right? As I have 5 more minutes, let's see how much more we can, clear up. I will delete this policy and go ahead with the next one. Let's see what we have. We have time to do this. Let's see. 6LZ, blah, blah, blah. Okay, we'll give it a shot. So you notice from the diagram I showed you in the thing, in the slide, we have service D is getting called from service C. What if you have a policy that says allow only service C to call service D? Don't let others call, right? Doing this in code gets very complicated, right, as you scale. So it has an layer 7 policy concept, right? The waypoint proxy will implement this. Restrict service, right? This one. What does it say? It's saying allow only service C. This is the declaration. It has a certain standard way, right? Cluster name, namespace, right? And then a service account name. So allow only service C, allow only get calls from service C to be invoked on service D. That's all this is saying, right? Declarative, right? I will apply this. And now, let's see how it works. You see what happened? Curl is running, it's a separate microservice running in the same namespace, but when I call service D, it says access denied. Ditto for calling it from service A or service B. I'll show you just one. Right? Access denied. And you call it from service C, it should work, right? Clear so far? So again, you have all these flexible policies, and it may change, right? Tomorrow suddenly they'll say, okay, allow A to call D, but not allow others to call. So it's easy to declaratively change and apply these policies without changing source code or redeploying. Let's see if we have 2 more minutes, what else we can do? Traffic, yada, yada, yada. Okay. Okay, let's do traffic mirroring. Okay, let me apply this first and then tell you what is happening. So we have V1 and V2, right? We have V1 and V2 of the service D running, and oops, this one. CTL logs minus F, right? And so you notice what I've done is traffic mirroring is what? I'm saying send everything to V1, right? This is called dark mirroring, this pattern, right? Again, V1 is your stable version. V2, you are still testing out, you're not sure, but you want to test it in real world load, right? So all the traffic is going to V1, but V2 has received the request, done its processing so that you can observe what is the behavior of the system, right? But the responses from V2 are simply dropped, right? Makes sense so far? All the response from the client is coming only from V1, right? V2, you are kind of, you're making it do stuff, but that is just for your observe to see how it works. No response goes because you're still not confident V2. So this pattern is also very useful in production. Again, no changes to your source code, just with the flip of a button, applying a few YAML files, you can change traffic, you can do mirroring in a very elegant fashion. So I think we're almost out of time. I'll put up the code on GitHub and share it and upload it to the website. A few other things I wanted to show you. You can inject delays, right? This is called chaos monkey, chaos testing. You would have heard this term, right? Again, it doesn't matter, platform independent. programming language independent, right? You can simulate, you say, when you call service D, inject a 5-second delay, right? No matter who calls. And what happens to your system, right? And again, these patterns were pioneered at Uber, Lyft, Netflix, these kind of companies, because they have so many services. What they do is randomly they will go and inject a delay here, cause a 503 error here or a 502 timeout or something like that to see what happens to the system. And then they learned a lot of things, corner cases in a distributed system, and they figured it out. And doing this without, of course, any source code changes or redeployment, right? Okay, I think I've taken up too much time in the demo. Do we have time for questions, one or two? Or lunchtime? Nothing? So there's no questions, or you can contact me offline. Thank you for taking time. I hope you can take away some points and do further research. Very exciting technology. If you are looking for open source contributions and things like that, I have a little thing. You can. There are details in the slide. They're introducing WebAssembly as a way to sort of extend what the proxy can do. You can extend it. WebAssembly again is platform neutral. You can write it in Rust, C++, whatever you want. You can add incrementally, experiment with adding incremental service mesh capabilities. And also, if you're a university student, like I said, I designed this talk for college students. Look at the source code for Envoy proxy, zTunnel, and all. If you're interested in systems programming, right? Very elegant, very nice code, very close to the metal. Your classic systems programming, right? They're very worried about memory allocation, and, how what is the minimum they can do to, lessen the overhead, right? How they manage the packets, how memory allocation is done, deallocation is done. Very, very interesting code. If you're a student, I think in a final year computer science, for example, you want to really understand how systems programming is done, read the Envoy, source code, and also the zTunnel source code. It is written in Rust. You'll get an idea of, how it's able to scale to handle this many connections, to do MTLS with little overhead. They're also planning to introduce eBPF, right? Extended Berkeley Packet Filter, which is a kernel-based thing, so that you don't have context switches. It'll be even more faster. So exciting times ahead for the project, right? Once eBPF comes. So I hope you'll have learned something about service mesh. Thank you.